Hello, today we're going to talk about per unit calculation. So first of all, we need to understand why we want to do per unit calculation. Usually in power grid, there are many transformers to boost the voltage up from a generator here. And then we can transmit the power to faraway areas, like in a city. So once we reach the city, we need a transformer to step the voltage down, and then to send the power to each household. Okay? So we will have many transformers along the way. For example, we can have this will probably just be say 10 kV. And then for us to transmit that to faraway areas, it could be like 220 kV. And then once we get into the city, we'll drop this back probably to say 66 kV or to 10 kV. And then when we use the electricity, we usually will drop that to 110 or 220. Okay. So you can see that along the way from the generator to the load, there will be many different voltage levels. So if we don't have a per unit value system, then we would have a lot of voltage levels. And then that is very hard for us to do the calculation if we want to calculate the current here. We would have to convert the current at this part of the grid to, based on the transformer turns ratio, convert that to the high voltage side. So there's a lot of trouble doing that. But if we use per unit value system, you'll see that we won't need to do that. We just use per unit value as if there's no such a transformer exists, okay? So first, when we do per unit value, we will have a base for the MVA base. So this is the capacity base. And then depending on which voltage level you're at, you can select a nominal voltage for that voltage level. For example, for if there's a 110 kV system, we can say, hey, use 100 kV as the base voltage, okay? So usually in power grid, we know that they are three-phase system. So when we say at this voltage level is 110, this means the line to line voltage, okay? So this is a VLL. So if we want to calculate the voltage base for line to neutral, then we need to use this voltage divided by square root of 3. Once we have the MVA base, we have the complex power, we have the voltage, we can compute for the current base. So the current base for three-phase system is using the MVA base divided by square root of 3 and divided by the line-to-line voltage, okay? So for the Z base, this is the impedance base, we can use the voltage, line-to-line voltage, the square of it divided by MVA base. So this would be the Y connected impedance. You can compute this way, okay? Okay, all that. Now let's just do a quick demonstration for that. Suppose that we have a system where we have the load, the load is a 60 MVA load. So it's 60 times 10 to the power of 6. And then the line-to-line voltage is 105. You can see that the voltage base actually is 110. So this line-to-line voltage for the load is 105. So this means that we can have a system. So this is the load connect to it. So suppose I have a load connected like this. So this means that this voltage is 105, okay? But the rated voltage base is 110, okay? And then the line to neutral voltage means that this is the neutral. So this line to neutral voltage is 105 divided by square root of 3. You can see that this is our line to line voltage, and this is our line to neutral voltage. Basically, it's 60.6 kV. Okay. So first, let's compute for the per unit value for the load capacity. So we simply use the load capacity, this capacity, divided by the base capacity. Okay, so you can see that 600 divide 60 megawatt MVA divided by 100 MVA, that's simply 0.6. Next, we can compute for the per unit value. This is not capacity, this is the voltage. So when we compute the per unit voltage, we use the line to line voltage, which is 105, divided by the base voltage, which is 110. So you can see that's 0.95 is the value. The other way we can see why when we use per unit system, we no longer worry about the line to line voltage or line to neutral is because when we compute for the line to neutral per unit value, then we can use this line to neutral voltage divided by the base. So line to neutral voltage, you can see it equals to 105 divided by square root of 3, but the base of the line to neutral voltage equals to the base divided by square root of 3. So when we have a VLL, this is a base value divided square root of 3, and then this nominal value is a V load, LL divided by square root of 3. So the square root of 3 will cancel out each other. Okay. So eventually, you can see that from per unit value perspective, if you computed it for line to line voltage or line to neutral voltage here, they are the same. So basically, we can say that the load voltage is 0.95 per unit value. Okay, so this is one of the advantage of doing that. So per unit value, it's the same, line to line or line to neutral in per unit value. But if you want to convert that back to the kV value, you simply times the different base value, like this one and that one, and then that will convert it back up from per unit value to kV. Okay. So next, we're going to compute it for the current. Similarly, the load current can be computed by using the load complex power divided by square root of 3 and divided by the voltage, the line voltage. So it's S divided by square root of 3, and then BLL, and then this would be the load current. Would be the load current flowing on the line. Okay. So once we computed this value in ampere, we can divide this value with the base. So here we can compute the base right here, and that base value is about 524 amps. So next, we can have another way of compute the per unit value. We can simply use the per unit capacity divided by the per unit voltage. So you can see that here we no longer need to consider the square root of 3. We can simply consider just using the per unit value power 0.6 and divided by the per unit value voltage, which is this value. Okay. And then compare these two equations. You'll see that if we use per unit value, we no longer need to consider the this is the line voltage, and then divide that by square root of 3 using the 3-phase MVA value. Okay, so this is another advantage of doing that. We can just treat this as a single phase circuit, use the per unit value power divided by per unit voltage, and that gave us the per unit value for the current. Okay, so this is another advantage of using per unit value. So after we computed that, the last part is computed the impedance. So the impedance again equals to the line-to-line voltage, the square of it divided by the capacity. And then once we computed this in ohm, we can use the this value divided by the base, which is right here. Okay, so you can see the base is 121, and then the load when you compute it this way is 183. So when this divided by 121, the base value is equals 1.5. So this is very straightforward computing. So next we're going to show you how we're going to use per unit value to compute for the voltage drop. So suppose we have this line impedance between this load and the circuit. So suppose we have a load right here. This is three-phase load, but because it's in per unit value, you can use single-phase circuit to represent that. You can see that this load is 60 MVA, 60 MVA, and then the power factor is 0.9 lagging, and then the voltage here is 105 kV. Okay, so this is our load. So we know also this line has an impedance in per unit value. This is per unit value 0.01 plus J 0.15. Okay, this is the impedance of that. So we're going to calculate what would be the voltage here. Okay. So first, when we saw that, we would know that, okay, we converted the voltage into the per unit value. We already mentioned that. We can simply use 105 divided by 110. So this is our voltage per unit value, okay? So we can have this V bounds per unit value. We said that the load bus 2 is this line voltage and use it as a reference. So when it is used as a reference, that means the 105 kV, and then the angle here is 0. So that's how we use the voltage as a reference. Okay, and then for the current at the bus 2, what we can do is that we can use the load, which is this value, and then times the power factor, because this complex power has a real power and a reactive power part. So the reactive power is simply B, this is real power times the power factor. And then because it is lagging, so this value, lagging means it's inductive. So the inductive load consumes reactive power. So this sign is plus. And then this is simply B 1 plus 0.9 squared. So this is computed for the reactive power. What is the sine theta would be, okay? And then once we have the complex power, we know that the load here with the power factor of this is gave us the theta value, and then this is the theta. And then it needs to be divided by, because this is three-phase power, it needs to be divided by square root of 3, and then divided by the VLL load, okay? So this is exactly how we do that. So once we computed this, this would be in amps, and then we want to compute this to per unit value. So we use this IBUS value. You can see that this value is in amp. So to convert the amp into the per unit value, we need to divide this by the I base, where we already calculated from our previous calculation, right? So once we do that, we convert this to per unit value. And then after this, this is another way to compute for the current, which you can directly use the per unit value to do computing. As we say that when we use per unit value to do computing, we no longer have the square root of 3. You can see we don't have this anymore in here. But this voltage is still in per unit value, and then this is still in per unit value. and then the power factor would still be here, okay? But it's just in per unit value, you no longer need to divide by square root of 3. So you can see that both results, it gives us exactly the same per unit value for I. So once I have the I value in per unit value, right? We have this I value. We can use this value times this impedance right here. And then that will compute for the delta V, okay? And then when we add the delta V with this is the V load plus delta V, we will be able to know what is this bus 1 voltage be, okay? So that's how we compute the bus 1 voltage in per unit value. So you can see here, after you get the per unit value, also we can convert them back to the kV value, because you usually want to know, well, what exactly is this value in kV? So this is the magnitude of it. We can simply use ABS, and then we can times back the line to neutral voltage. So if we use the line to neutral voltage base, then the way you compute this magnitude is for line to neutral voltage. If you use the line to line base, then this value computed will be the line to line voltage, okay? And then for the angle, it's easy. You can just use an angle and then take this value, whatever this complex number have a angle, then that will be your voltage angle. So you can simply take an angle. The reason I put a radius to degree here is I want to show a degree value. So this result will be in degree. If you don't have this part, then this value will be in radius, okay? Okay, that's what I want to say about this lecture. So a lot of students tend to mess up with the per unit value. So if you can go over this example and then play around with it, just change the different voltage base value, the MVA base, you will see that you can get a different result. And then this part just shows you how to compute using per unit value the voltage from one bus to another, and then convert the per unit value back to the actual value and then the angle. Just so you can see that what's the difference, because a lot of students tends to forget to convert that back. You can see that if you don't put it here, you can run that. Oops. Okay. So you can see that when I run this whole code again, this is the difference. If you don't put a radius to degree here, you only use the angle, then this is in radius. But if you put radius to degree, and then this would be the angle in degree. So depending on what you want to see, for me, it's I like reading degree, because from 0 to 360, if this is in degree, I have a better understanding where the angle would be at. But if you're familiar with the radian system, then you do not need to do that. Okay.